Okay.
So, good evening, students. Welcome to week 8 problem solving session for Analog Electronic Circuits course. I'm audible clearly, right? If you can confirm.
Yes.
Okay. So, in today's session, we'll be talking about poles, zeros. We'll be dealing with capacitors in this particular session. So, let's begin the session with the first problem that we have. So, if you have any concern, feel free to unmute yourself and ask, and interrupt me anytime you feel like. So, starting with the first problem, in this problem, we have a circuit given. So, if you can observe clearly, until now, yeah, until now, we had a resistor over here, right? So, here we had a resistor and a MOSFET, and we called it as CS amplifier, correct? When we had resistor at top and there was a N-type MOSFET at the bottom. But we were discussing it a few weeks ago that in CMOS technology, we want all of our components to be made up of, um, first of all, MOSFETs, and secondly, the resistance that we can obtain from an active load. See here, you observe an active load. So, active load basically means active transistor. So when you use transistor as a load, we call it as active load. The transistor. So here basically you are using transistor to obtain the resistance. We know that the resistance obtained by a transistor over here from this particular node is 1 upon GD, right? And this value is very high. And we also know that to get a larger resistance, if we design a resistor, let's say it's a wire bound resistor, so to obtain very high resistance, you would need very large resistor. So the resistor size increases. So in order to minimize our device size, that is the dimension, which is one of the major factors while designing a chip, we go for active loads. So that's why here, instead of a resistor, this N2 transistor has been connected. Now, moving on to the problem. In this particular question, so there is a circuit of a CS amplifier with active load and with stable biases. The value of device parameters have been given. So let's quickly note down the parameters. Okay. Along with that, we have R1 of 90K, R2 of 30K, R3 of 60K, C1, C2, 10 microfarad, and C1, C2, 10 microfarad, and CLS 100 picofarad. And we have been given this CGD is 10 picofarad, CGD of 10 pico, and this is CGS of 5 pico. VDD is 12 volts. Okay. So this is the total circuit that we have. In this problem, refer to the given circuit. Find the DC gate voltage of transistor M2. So it means we need to find VG.
So I have a question.
Yes.
When you said like all the transit, I mean in a circuit when we have all the transistors, sorry, all the loads which we make through transistor, then what
Hmm.
about this R2, R3, and so on, these
So
resistors? So,
here basically we are using resistors, but I mean in your circuit, if these are not internal biases, so if this is not an external circuit, it's an internal circuit, then most probably this is also made up of transistors. Most
okay,
transistors if it is inside the chip. But if it is something which you are connecting externally, like if you have external circuit, so there you can use resistors and capacitors, right? But if it is
right. Yeah.
inside the chip, it is most probably like it would be made up of your transistors only. So resistors will also be converted to transistors, and those transistors will be used.
Okay, thank you.
So basically, if you can use a transistor in linear region, so it is a resistor, right, in a linear region.
Yes, but the resistance is not very high, right, in that linear region. I mean,
I
if we
mean,
need a very
so it will depend on this, right? So what is your biasing, doping of the transistor, all those things.
yes, I mean
But
the
yeah,
transistor
so
characteristics.
yes. But the basic idea is inside a chip, when you are going for an IC designing, you try to first of all use what is uh, already present in your technology. So if you have a MOS based circuit, like everything is made up of MOS, it is easy for you to place them properly and design the circuit, right? Compared to very different components, because each component has different size. When I talk about MOS transistors, it is basically in few nanometers. Talking about the very recent technology node, you would be having your MOS transistor like length from source to drain. It's around 12 to 15 nanometers, max to max.
Okay.
But when you
Uh,
talk about resistors, you imagine that wire thickness you would need is still quite high. So getting a 60 kilo ohm resistor, how big that resistor would be if it is a wire bound resistor. So that's not feasible for an IC, right? So that's why
uh,
we make sure that we use the components. So we try to design the components made up of these small components, which are the transistors. So the whole circuit is made up of transistors. That is the basic idea. Even we draw capacitors out of them. So you can have
uh,
like metal semiconductor and highly doped, like if you have a substrate with source and body like grounded, then you have this MOS capacitor, right? And you
yes.
also know the value of MOS capacitor. So from there, that particular configuration can be used as a capacitor inside the circuit if you want a capacitance. So yeah.
Right. So, can we obtain like these large values using transistors like 90K or in mega?
Um,
I mean, in the linear region, particularly with if we go to such small nodes, let's say, like you said, like they're 12 to 15 nanometer, because
I
if the length
mean,
is small, the resistance would be small, right?
yeah, but the resistances, majorly it would come from your mm, depletion region. Region will give you a lot of resistance. So drain side depletion region will give you a lot of resistance. And then if you still want even higher resistances, then you can use gate side, because we say that there is no gate leakage and everything, but there is still gate leakage. So when you want very large resistances, say in mega ohm or giga ohm in that range, You can use, I guess, the oxide resistance that will come from your device. That
Yeah,
can be used because
gate
gate
side would
leakage
give a
will
capacity.
start coming. Sorry. Yeah,
I'm saying
gate
like gate
is,
side will give a capacitance which should be
yeah, but
undesirable.
if it starts like conducting current, so that's where I'm saying. So, like, if you have a gate current possible in your circuit, so your MOS design is such that it can conduct current. So if it conducts current, then it is not a capacitor, right? At that time, it will behave as a resistor. And that happens when the biases are such and the gate, like the current is very small. And it's almost like when you obtain your close to breakdown that range. But I'm not really acquainted with the values that we can get out of MOS resistors. But
Right.
I'm very sure that inside your chip, we try to use MOSFETs as much as possible to compensate for all the devices,
Right. Okay.
like all the be it a
Fine.
capacitor, resistor, so basically all the components. Yeah.
Okay. Okay. Fine. Thank you.
Okay. So yeah, coming back to the problem that we are in, so we have to find VG2, and it is set like asked that we can assume the meaningful value of R4 to get the DC gate voltage at M2. Before starting this, okay, so yes, this is our circuit. In this circuit, we have to find VG2. So VG2 is this gate voltage. So basically, this is what we need to obtain. Now, first of all, we can find this VG1, correct? So this voltage VG1 is 12 into 30 upon 90 plus 30. This is 12 into 30 by 120, 10, 3. So VG1 is 3 volts. Now we know in a path from VDD to ground, only single current will flow. That makes us conclude that ID1 would be equal to ID2. That means okay, Kn W by L1 VGS minus VTHN whole square equal to Kp W by L2 VSG minus mod VTHP whole square. Here we are given with the values zero point 0.5 to 0.5 VG3 minus 0 minus VTH is 1 for both the transistors whole square equal to 2 Vs is 12 minus VG2 minus 1 whole square. So this is 4 equal to 4, 11 minus VG2 whole square. Okay, so VG2 11 minus VG2 is plus minus 1. Now here, let's say if we consider, so here you can have two cases, like you can have plus 1 or minus 1. So we will obtain what is correct out of these two. So let's say for plus 1, what we will get is 11 minus Vg2 equal to plus 1 makes Vg2 equal to 12. Now see, if Vg2 is 12 in this particular circuit and S is also 12, so this is
Mhm.
source, this is gate, drain, this is gate, source. So if gate and source are at equal voltage, then VGS becomes 0. But we said that our transistor is in saturation, right? So the assumption is transistor is always in saturation to give us this amplification operation. So all the transistors are in saturation here. So, but here the transistor is not even turned on. So you cannot have this particular condition, right? So that's
Yes, that
why
is
this
-1.
is, yeah, so that's why the correct answer is minus 1. Now, when we use minus 1 and we try to obtain the gate voltage, we get VG2 as 10 volts. Now, when this
Uh,
is 10 volts, so your VGS2 would be 2 volts, or
yeah. Uh,
I should say
so just a
VST.
small correction. That
Yes.
is -1 in the first case and +1 in the second case, I guess.
Uh, yeah. So this is, uh, so basically VG इधर जा रहा है ना? So yeah, so this should be हाँ थोड़ा सा minus 1 and this will be plus 1, right?
Yes.
Yeah, so this is plus 1 and here it should be minus 1. Correct. So basically the
Uh,
idea is that we need to get some VGS out of it. So we
yes.
have
So just
first,
I had a
yes,
small doubt. Like we
huh,
use the VGS equation in this, like just the
yes,
quadratic one.
yes,
Why didn't we consider the channel length modulation? Lambda was given, right? Lambda is given for
yeah,
both
lambda
the.
was given, right?
Yeah.
Good question.
So
So basically, see, the idea is here, what are the things you know? So when you are only considering VGS equation, you have a single variable and a single equation you can solve easily. But when you are going to use the lambda equation, you don't know VD, right?
yes.
So there would have been another variable that will come into picture. For that, you would need another equation, correct?
Yes, definitely.
And how would you find that equation?
I mean, yeah, there is no other
There is no
means.
other like there is no other way we can proceed, right? Even if we
Yes.
knew like VGS, so we would have considered, let's say, VDS to be VGS minus VTH to be in saturation to start with. But we don't have any condition over here, right? So how do we go ahead? Correct?
Mm,
And
yes.
secondly, why it is safe to assume that way is because if you observe the lambda values, they are 0.01 or
Okay.
0.015 times VDS. So VDS will be definitely a small value, correct? Let's say
Yes.
if 12 volts is here and we can say, okay, half is being depleted, like half is being consumed by your PMOS and half for NMOS, then also it would be 6 volts. And when it is
Yes.
multiplied with 0.01, it would be a very small value.
0.06.
So,
Yes.
yeah, so it's like safe to neglect. And it's also a
So
way to observe. Yeah.
like when it's like two decimal places down, then it is safe. But let's say if it is like point 0.1 or 0.15, so that is just one decimal. So
Uh,
in those cases, there will be some error present, like due to our. I mean,
some
we
error
cannot go any
present.
other
Yeah.
way, but
Yeah,
some error
but
will be there.
yeah, so that's why, see, like in this particular question, considering the given values and the way I can proceed, I have neglected. But there is a possibility that in the next question, I might not be neglecting that. So
Okay.
it depends on the problem, and basically the idea is, first of all, you should be able to solve the problem, right? So
Yes.
what is the way to go ahead? Because if I would have considered like lambda VDS term as well, but the point is I don't know VD. And there is no other relation from where I can find VD, right? Because there
Yes.
is no direct relation that can give you the value of VDS. It's always relative that we assume, right? If we have to even assume, we consider the saturation condition and limiting saturation condition. From there, we start and we get VDS. But unfortunately, here we didn't even know the gate voltage. So, if without knowing the gate voltage, finding VDS is very tricky. That's why.
Mm.
So, yeah,
Okay.
so basically, questions are also designed in a way, keeping in mind the solvability of them theoretically, if I'm talking about theoretical problems. But yeah, in real life, if there is a problem, then things are there to deal with it. So, that is a different scenario. So, like, let's say if you are using a tool, so in a tool, you know all the values at each and every point, right? So
Yes.
there, the problems you deal with are completely different compared to how you deal with in a theoretical setup.
Okay.
So yeah, that is the thing. Okay?
Right. Thank you.
Yeah. So now moving on to the second problem. So it's a continuation of the same problem. So in this problem, we are asked to find the value of R4. So this R4, if you observe, it is connected to V out, right? So this particular R4 is connected to V out. Now here, let's say if I know that ID1 equal to ID2, and from there, KMW by L1 VGS1 minus VTHN whole square plus lambda n VDS1 equal to QPW by L2 VS32 minus VTH.
Sorry, just one more question. So in the last question,
Yeah.
we considered that ID1 is equals to ID2, right?
Yes.
Sorry, was the biasing the same? So some current should have flown through R3 and R4 also, right? So can it be not like how are
Yeah, we
these equal?
assume that it's negligible. We assume that it's negligible. And with that assumption, so in this problem, if I talk about the assumptions that we have taken, so A, current through R3 and R4 is negligible, and B, all transistors are in saturation. So these are the two
Uh,
assumptions that we have basically considered
yes, just want
to
to
solve it.
like clarify one thing that
Yeah.
I mean the possibility of assumption that current through this 60K and R4 like this is negligible. Are we assuming because the MOS from its source terminal on the PMOS from its source side
Mm.
is offering a
Mm.
lesser resistance compared to that side? Is
Yeah, you
that
can assume it that way. And also, see, um, the basic idea is you want amplification, right? What is
yes,
the circuit that is basically providing you amplification is the transistors. The series transistors are the main circuit that are providing you amplification. So you want whatever voltage you are providing, the maximum voltage, that is the supply voltage, should go to your amplifier circuit rather than your biasing circuits, which are these resistor circuits. So that's why you would observe that these resistors are too high. And since in this problem we are going to calculate the value of R4, right? So here
yes.
you would clearly observe like observing the value of R4. So you would have R3 and R4. So from there, if you calculate the value, it would come out to be very small.
Okay,
Because the design idea also comes from there that you always want the maximum power that is provided by your supply to be dropped across your amplifier main circuit. So you want very minimal wastage. So because biasing circuit, the power consumed by the biasing circuit is a wastage, right? You don't
Yes.
want your power to be wasted. So
Yes.
that is the idea behind design also. So when you design also, you keep that in mind that you're biasing the circuit. All of them almost together should not consume more than 10% of your total power dissipation. So you design that
Okay.
way as well. Yeah. So moving on with this problem. So here now, see, we know the gate voltages now. So I can safely consider the drain voltage because here we'll only get again one variable, which is V out. Correct? So from this equation, I can simply find the value of V out, right?
There should be one lambda and VDS1 and lambda P VDSD2, right?
Here N is VDS1, lambda P VDS2, right?
Yeah, it should be 1 plus or just. I didn't
1
understand the equation.
plus, oh, 1 plus lambda, right? Oh, yeah,
Yeah.
matlab, lambda
It looks like these
zero
are
point
two
0.5.
different terms in one system, like plus this.
Okay, okay, so maybe 1 plus um, okay, so plus lambda VDS1. Let's write it in a more familiar way. Plus lambda P VDS2, right?
Uh,
Yeah,
yeah,
so now,
these sorry. I
huh,
mean, there should be no plus sign in before, right? 1 plus lambda P. So bracket 1
yeah,
plus lambda into
it's
VDS.
multiplication, right? ID
Yeah, yeah,
into 1
yes.
plus lambda into VDS. Yes,
And
yes.
VDS, yes, yes.
Yeah. So
Okay.
basically, now simply we'll substitute the values. So here we have zero point 0.5 into VGS1 was how much? It was 3 volts minus 1 whole square 1 plus lambda n is lambda n is 0.01 into 0.01 into VDS1. So VDS1 I
Uh,
can simply write V out minus 0 equal to 2 into VSG, that is 12 minus 10 minus 1 whole square, 1 plus 0.015 VSD. So that is VS is 12 minus V naught. That
that is
is
just like lambda into VDS. There is no bracket, I guess.
where
0.01 into, we have put a bracket, like 0.01
point.
into, it should be directly into V out
Yeah,
minus
yeah,
0.
it's a direct into, but it is VDS, right? So I have separated VD minus VS. So that's why I wrote it like this
Because
to
it's
bring
looking
in
like 1.0, 1.1, that whole plus into VDS.
where
Yeah, yeah, now, yeah, now we can put up. No, no, this bracket. I don't think this bracket should be there, right?
1 plus. Acha, acha, this extra bracket. Okay,
Yeah,
okay.
yeah,
Yeah,
that
yeah, yeah.
that was confusing.
Acha, acha, acha. Tick, 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 tick. Now it's fine.
Yes, yes.
Okay, so here also, so this would be whole bracket.
Yeah, that happens sometimes.
Yeah, वो writing में ना, sometimes
Yeah.
a little. Anyways, so this is out into A. 1 plus lambda radius. Now, okay, right. So now here, this is 0.5 into 4, 1 plus 0.1 V out. into 2, 2 into 1 into 1 plus 0.015 minus 0. So we are left with 1 plus 0.01 way out, and this side we have 1 plus. So this is how much is 12 into 0.015?
0.18.
Okay, so this in this cancel, we have V out into 0.01, 0.015 equal to
Uh, 0.18.
0.18, 0.18. Okay, so this is 0.18, then V out would be 0.18 by 0.025. So how much is the value of V out? What is the value of V out?
7.2.
7.2 volts, right? Okay. So if V out is 7.2 volts, then yeah, if V
So
out is
basically, sorry.
yes,
So basically, the methodology is like we always need to have a VGS. We need to find it out. So like here,
yeah,
if
more
we
or
had
less.
applied, yes,
Yes,
yes. So
because VGS only defines, first of all, whether your transistor is on or off. Secondly, is it
uh,
in, yeah, so is it in saturation or linear? So a lot of information is obtained based on your VGS. So VGS needs to be known to you ideally because,
uh,
and also all the equations that you have are basically based on VGS. We don't have direct equations based on VDS as such,
right.
right? So that's
Yes. So I was saying like in the first case, we find out VGS using a
yeah.
simplified equation. I mean, without
Yes,
considering the
yes.
lambda effect. And
Lambda,
then we use
yes,
that same VGS in the second one using
yes,
all the effects to find out the value of R or V out.
yes, yes.
Okay. Okay.
So it's like
Fine.
building it step by step. Because if
Okay.
I would have directly gone to this particular formula in the first question, now the concern is this particular formula would have two variables. One is with respect to that V out and other would have been VG2. Now solving two variables using one equation is impossible. For two variables, you would need two equations, and you
Yes.
don't have another equation over there. So that's why.
Okay.
But yeah, the question would have been a little different if there would have been some more information given, which would have supported us with the second equation. So ideally, it boils down to you would need another equation, right? If you would have
Yes.
some information, let's say the current through your R3 and R4 was given, then I
Right.
can safely use it, right?
Mm-hmm. Yes.
So
So
it's basically how the question is formed. Depending on that, you solve the problems. So it all depends on how the questions are formed and how
I
you
mean,
can
so
approach a question.
yeah, so basically, as a rule of thumb, if we have just one equation in such kind of questions, and we are not able to obtain any other second equation which links VDS to this thing,
Hmm.
so better to go for first the simplified thing, right? Just take one this thing
Yeah,
and
better to go for that because also the thing is, as I said, lambda is very small value.
right,
Most of the times it is 0.01, hardly it is zero point 0.1. Most of the
right.
times it is 0.01, 0.02 in that range only. So it's safe to ignore as well.
Okay, okay, fine, got it.
Yeah,
Thank you.
that's okay. So yeah, since we got our V out, that is V out is 7.2 volts. Now I have to find this R4, correct? I know this voltage, I know this voltage. So what I'll do is, let's say at x, okay, I would write a KCL at x. X is basically VG2, right? At this, I write a KCL. So how would that KCL would look like? So it is VG2 minus 7.2 by R4 plus VG2 minus 12 by R3 equal to 0. Because there won't be any gate current, so this current is 0. So here you know the value of VG2, which was um, VG2 was 10, right? Yeah, 10 minus 7.2 by R4 plus 10 minus 12 R3 0. 2.8 by R4 equal to 2 by R3. So R3 equal to 2 into oh, sorry, R4 equal to 2.8 2.8 into R3 by 2. So R4 would be 2.8 times R3 was 60K by 2. So 30K. 84 kilo ohms, right? Now, if I talk about, okay, the current that is flowing through this would be how much? So it is 12 minus 7.2 by 60 plus 84K. So what is the current that you are obtaining from this? Is what is the value that you get?
33 microampere, I guess.
Yes. So see how small this current is. This is 33 microamperes, right? Whereas if you look into this particular current, like normal this current, so how much is this current? This is in um, zero point 0.5 into 4, so which is 2 milliamperes. So compared to 2 milliamperes, which was ID around 2 milliamperes, this is much smaller, right? This current, this is very small. So that's why we say that you can neglect that. And also, it is a rule of thumb while designing also that you make sure that all the circuits other than your MOS transistor circuit should have like less than 10% of total power dissipation. So that is the idea. You should not lose much power in your supporting circuits. This is clear?
Right. Yeah. Got it.
Yeah, okay. So again, to the next problem. So this is for the same circuit. In the circuit, again, we have to find the voltage gain in the mid-frequency range of amplifier. So since we know that this is a CS amplifier and gain is GM into Z out. So Z out should be calculated here with respect to this. And GM will be with GM, GM of transistor 1 or transistor 2 while finding the gain.
Uh, that should be the where the input is there. That is transistor one.
Yes. So it should always be GM1. So from there you would find GM. So GM is kW by L, which is 1 minus VTH So this becomes 0.5 into 3 minus 1, that is 2. So GM becomes 1 millisiemens. When we talk about Z out at this particular point, so if we observe
So
this carefully, here you would get Z out. So 1 is R naught 1, that would be coming because of transistor 1. Parallel to R naught 2, you would have because of transistor 2. Now, there is another resistor, this R4 resistor, which is also connected, correct? And you
yes.
know at this particular gate, it is DC grounded. Sorry, AC grounded. This is also AC ground. And this particular node where gate is there, that is also AC ground because we consider that there is no AC going there, right?
Uh,
So assuming that you would have R4 in parallel because it is like so this
mm,
particular this particular resistor is connected between source drain gate, right? So this is a Miller resistor. So this is a Miller resistor R4 for M2, correct?
yes. So, I mean,
So
shouldn't
R4,
R3 plus R3 plus R4 be parallel with this thing? I mean, because no current is flowing. If we consider, oh, this is AC ground. Yeah. So C should be short circuited, right? C3.
C3, where is C3? Uh-huh. Yes, also C3 is short circuited. So from there, you can directly see that since this is AC, so ये short circuit होने से R3 would not come into picture. Or if also you look at it like it's a Miller resistor, then also you would get that. So if it is a Miller resistor, we know that in input side, the resistance comes out to be gain times of the resistance value, like approximately gain times. So if it is a Miller resistance, input would be approximately A into R4, whereas output side we would only get R4 approximate values, correct? And from
Yes.
there, and since we want it at the drain terminal, which is at the output terminal, so the resistor, the almost approximate resistor would also have the R4. From there
Uh,
also you
but
would get that.
but this particular resistor is a Miller resistor for
R2,
M2 and
M2, yes.
yeah, M2, yes. And so like this gain, the gain, which gain will it be? Should it be of just two or like
It should
the
be of 2. It should be only of transistor 2.
okay, but then I
Because
mean
वो किसके corresponding मिलर है उसके लिए ना, so that matters, right? And but you
yes,
don't
but
have to worry about the gain, no, anyways, because you know that it is coming at the output, and output side you would only have it as a factor of 1 because it is
mhm,
like 1 plus 1 by A, so we know that A is definitely larger compared to A. So
right.
that's
Yes.
why we write it as almost 1.
Okay.
So from that also you would get that. And since here there is this extra capacitor, so from there it anyway shorts. So R3 will be shorted. So from there directly you can write R4. Both are fine.
Okay.
Correct?
Yes.
So yeah, R naught, we'll calculate the values for R naught. That is R naught is 1 upon G naught 1. That is 1 by lambda ID, lambda 1 ID. And we already found out this ID was how much? 1 milliampere है क्या? कि 2 milliampere?
That was approx we took, I guess.
इसको भी consider करना पड़ेगा क्या? No, but still,
That would make
this
it more.
point 1.24. Isn't it 2 milliamperes?
Um,
यहाँ से कितना आ रहा
two,
है? 2 into 2 minus 1. Yeah, it's 2 milliamperes, right? Okay. Yes, ID1 is 2 milliamperes. Because I made some mistake. Resolving. Anyways, so ID1 equal to ID2 is almost equal to 2 milliamperes without considering that channel and modulation. So
if we
from
consider that, it is like 2.2, 2.22
yeah, very
milliamps.
small, very small. So anyways, so this would be 0.01 into 2 and R naught 2 is 1 upon 0.015 into 2. So what is the value of R naught 1 and R naught 2? And we know that R4 is 84 kilohms.
R1, R01 is 50K, and
50K. R naught 2,
that is 33.33K.
33.33K. And this is 84K, right?
Yeah.
So what should be your this thing? Z
That be
out,
less than.
which is R naught 1 parallel R naught 2 parallel R4. So what is the value that you would get for Z out?
Uh, Somewhere around 16.15K.
16.15K. Okay, so you can basically
Approximately.
calculate, right? So approximately how much is it? 16.15. So if it is somewhat around 16.15, so your gain would also be minus 16.15 volt by volt. And if you have to find the gain in dBs, how much is it in dBs? So you have to use
24,
20 log. It is
24. Yeah,
24?
yeah,
Okay, so it is 24.
24.16 somewhere.
24.1. Okay. So this is the gain. So basically you understand the idea, right? How we go through.
Yeah.
Yeah. So it's about how you solve it. But values are okay, fine. You can anyways calculate them. But the
So
procedure is important. Yeah.
just one small doubt. So the Miller capacitance which we are considering in this case, what
Uh,
will we consider as the output and what as the input? So the
where is the
output side will be considered the output. Is that so? I mean
sorry, I
the
didn't.
drain terminal.
Drain is always the output, right? Considering the CS configuration.
Okay, yeah, I think yes, for both of them, even for M2 drain is the output.
Yeah.
So okay. Yeah, so it's simple. But there might be cases where, let's say, I mean, there can be one transistor, let's say above M2, let's say M3, and if we have
Hmm.
a Miller capacitance or Miller resistance over there, what
Hmm.
will we consider as an input side and what as an output side in that case?
So
Because
it depends
that
on is
value
it
will change.
even coming into your picture? Like what is the path you are taking? And based on that, it will be considered. So maybe when we will do multi-stage, so after these we will be solving multi-stage, maybe in coming sessions. There you would observe such kind of problems where you would have cascade configurations, one above the another, and how do we solve that? So it will be clear over there.
Okay. Fine. Thank you.
Okay. Yeah. So moving on to the next problem, again, see it's connected to the same previous problem. So here you have to find the input capacitance of the amplifier circuit shown in 8.2. So input capacitor, you know, if AC signal is given, this would be shorted, this would be shorted, and this would be shorted. Now, when you have to find the capacitor, so what capacitor I'm talking about is this. So this CN capacitor, what it would consider. So we know CN would have CGS plus what would it have? This Miller capacitance, CGD. And it would be almost gain times CGD, correct? Because of the Miller effect. To be very accurate, it would be 1 minus A into CGD. Now, this gain is actually the gain of the amplifier, right? So, okay. So here, because this is output and this is input, so the gain that you will obtain is basically because of like whole circuit, right? So here, since output terminal is common, so it's more like GM is coming from okay, this transistor, but Z out at this point output node, it will have both. So here the gain will come this gain. So this total gain that we have obtained, that only will be appearing over here. So this particular one will be 1 minus 16.15 into how much was this? 10 pico. So this becomes 17.15 into 10 pico. So CGT 1 minus A. So here rather than maybe 1 minus A CGT. So 171.5 pico and CGS is 5 pico. CGS is 5 pico. So CN will be 176.5 picofarads. Yeah. So this is clear, right? Because in the circuits gain, first of all, we have used the GM of this transistor only, and Z out will be the output terminal's resistance. So in this particular Z out, you would observe the behavior because of like impedances due to the presence of both the transistors. So that's why we would directly use the gain from the whole circuit here.
Right.
Okay?
Uh, yes. So, let's say, I mean, in this case, we will look from the source, which is Vn, directly the capacitance that we are seeing, right? Because even
Yes.
if we go a bit further ahead, then C3 is also into picture, but that is not in the direct path, so we
Yeah,
won't
yeah.
consider anything.
We won't consider that because that's why it is important. When it is said capacitance or input of something, you will look from the input terminal. Like where is your input port? From there, what are the components which are coming into picture? You would only define or talk about them. Similarly, in output case, what are the components that come into picture?
Right. Okay. Got it.
Yeah, that's
Thank
all. Okay, so moving on to the next problem. So in this problem, you have the circuit with op-amps where R1 is 4.1, R2 is 1.3, C1 is 7.4, C2 is 8.3. Okay, assume op-amp has very large gain. So what is the location of poles in the transfer function? So you see, simply we understand that in op-amp, If you provide input here, then okay. So you have two different scenarios. One you provide input here, other you provide input here. This is inverting configuration. This is non-inverting configuration. We know in inverting configuration the gain of the op-amp is minus Rf upon R1. In inverting configuration the gain is 1 plus Rf upon R1. Correct? Now, by looking at this particular circuit which is already given to us, what type of configuration is this? Is it inverting or non-inverting?
Inverting.
Inverting, right? So this
Yeah.
is inverting configuration. So when this is inverting configuration, we can simply consider like this particular as Z1 and this particular combination as Z2, and we can find gain as minus Z2 upon Z1. Correct? Because it is a similar configuration, right?
Yes.
So now, so in this particular problem, it was asked that what is the pole of the transfer function? Similarly, what is the zero of the transfer function? So basically, in the same question, you have to find the poles and zeros of the same same circuit. So we know when there is a transfer function, the value of s for which TF equal to 0 is 0. When values of s for which TF becomes infinity are poles. Correct? We know this, right?
Yes. Yes.
So now here let's find the transfer function. So how I would write it is I would write it like so when you take the transform of capacitor it becomes 1 by SC1. So here it would be 1 by SC1. Here it would be 1 by SC2 in Laplace transform, and from there I'm writing the transfer function. Okay. So the transfer function or gain function, which is V out by Vn, would be minus Z2 by Z1. So that is R2 parallel 1 upon SC2 by R1 parallel 1 upon SC1. So R2 parallel 1 upon SC2 and R1 parallel 1 upon SC1. How would you solve them? So it is like 1 by R2 1 upon 1 by R2 plus 1 upon 1 by CS2 C2S 1 upon 1 by R1 plus 1 upon 1 by SC1. This would be 1 upon 1 by R2 plus C2S by 1 upon 1 by R1 plus C1S. Now here 1 upon 1 plus R2 C2S by R2 divided by 1 upon 1 plus R1 C1S by R1. So this would become like this would come here, this would come here, R2 upon 1 plus R2 C2S by R1 upon 1 plus R1 C1S. Now again these two will be multiplied, these two will be multiplied. So the final transfer function that you get is R2 1 plus R1 C1S by R1 1 plus R2 C2S, right? So now if this is your transfer function, you can simply from here find the value of poles and zeros, right? So this is pole and this will, oh sorry, this will give you zero since it's a numerator, and this will give you the pole frequency. So simply 1 upon R1 C1 is your zero frequency and 1 upon R2 C2 is your pole frequency. Is this clear?
Yes. So pole essentially reduce the gain and zero increase the gain. That's so.
Pole reduce the gain, zero increase the gain. How?
I'm just asking, like, I mean, in the transfer function, when we plot the board plot,
Haha, Bode plot, yes. Pole gives you plus 20, sorry, pole reduces your graph with a slope of minus 20 dB per decade, whereas zero increases your uh, this increases your what was I
gain,
saying?
uh,
Yeah,
amplitude.
gain or plot by plus 20 dB per decade.
Right. Like mostly we talk about the poles in most of the cases, right? I mean,
No, but in border plot you could have both, right? Poles and zeros because your plot will be based on that.
yeah. So if we have a circuit, then that means both of these are important, poles as well as zeros, right?
Yeah, yeah, yeah. Both are important equally.
Right. Thank you.
Yes. Just so that it's easier for students to analyze. So we got the idea, right? How we have to look for poles and zeros.
Yes.
And yes, so from there we can simply, so here my zero would be 1 upon R1 C1 and pole is 1 upon R2 C2. This will come in radians, okay? So make sure you are using the um, units correct. So now if I want the value in hertz, so it should be 1 upon 2 pi R1C1. This result will come in radians. Is this clear?
Yes.
Okay, so with this, let's move on to the next problem. So in this particular problem, we have this circuit below with K of 86 millisiemens per volt and lambda is zero point 0.1 volt inverse. Gain is 554, RL is 43 ohms, and this VDD is 1.2 volts. So now what is the output impedance? Output impedance means looking from here set out. Such that give them in milliohms and do not disconnect the op-amp while computing this input impedance. Okay, so in this particular problem, whatever the ID is, ID would be V out by RL, correct? Now, since it is an op-amp, input is 1.2 volts. This is 1.2 volts. Since it is an op-amp, considering the gain is still very high, we will take this point also to be 1.2 volts. That means output is at 1.2 volts. So 1.2 upon 43 ohms. ID turns out to be how much? 27.9 milliamperes. Correct. Now, in op-amp, how does the output look like? It is gain times V plus minus V minus. Okay. So if I talk about this particular circuit, considering that there is no input in the negative terminal, right? So V out is we want to calculate Z out, right? So let's see how can we do that. So Z out means let's suppose I apply Vx over here, okay, and put this to AC ground because I'm doing AC analysis. So if my voltage over here is Vx, that means this point is Vx. So from here, if I want to find what is my output over here, op-amp's output, that would be A times 0 minus Vx. So V out would be minus of AVX. So here it would be AVX minus AVX at the VG, right? Now what I'll do is I'll find the small signal current. So this is IX. Okay. My Z out, I can write it as Vx by Ix. Correct? Based on this particular circuit that we have designed. Now here we know that small ID in a transistor is Gm into small VGS plus GD into small VDS. Correct? So this is this being a N-type transistor. So this is drain, source, gate. So, and since it is AC analysis, so this would be grounded. So this becomes GM. VG is minus AVX and VS is VX plus GD. VD is how much is VD? VD is 0 minus Vx. So ID, small id becomes like this. Now, if we observe very carefully, ID is coming from here, right? And here, considering that there is no current flowing inside the op-amp, like input terminal of op-amp will not have any current. So whatever current ID is flowing, so it means Ix that is coming from Vx is also being distributed across this um, transistor current, and the same is flowing through resistor also, right? So I can safely write ID as minus Ix or Ix as minus of ID. So my Z out was how much? It was uh, Vx upon Ix. So it can be written as Vx upon minus of ID. And from here, we can find, I have to separate, let's say, Vx. So how it would look like Gm minus Gm1 plus A minus Gt. So Vx upon ID is or minus भी ले लेंगे तो Gm1 plus A plus Gd. So this is our Z out. Is this clear?
Uh, yes. So, I mean, when we are looking at this one, um, usually should RL not be in parallel with this thing or
RL?
a complete Z out?
Yeah,
Maybe.
for complete Z out, I mean, this one would also do. So maybe what you people can do is you can find GM and G2. I'll be back after drinking water, okay? Did the screen go off?
Yes, we cannot see anything.
Oh, okay. So yeah, yes. So the idea is, okay, if we go by that, then rather than writing it like this, maybe I can write it like, so this is ix, this being ix1, and this being ix2. So let's say my ix is equal to ix1 plus ix2. So in that case, my id is equal to minus ix1. And yeah, this will be ix1. So this will be z out 1 and in parallel. So uh, z out would be z out 1 parallel RL, right? To be precise, like if we say, okay, okay, all the currents are being distributed perfectly, so then I can write like this, and this one will be 0 because there won't be any current going inside your op amp. So yeah, we can write it like Z out to be the current, the impedance that we are getting. So this is Z out 1 from here, which is parallel to RL. Like this we can write. Oh, camera. Yes. Is this clear how we solved this?
Yes,
Yeah. So in the similar fashion, now everything is same. It's just that in place of NMOS, you have a PMOS over here. So for the case of PMOS, now we have to solve the equation. So it's like the procedure is all same. How we did for NMOS, the same way we will do for PMOS. Here again, you have to find the output impedance. So you will use a Vx. So this Vx will provide me with some Ix. Here I would get my ID. And here I would get, let's say, Ix1. So my Ix is minus ID plus Ix1. Z out should be Vx upon Ix. And here again, the small ID would be Gm Vsg plus Gd Vsd. So that is Gm Vs. So this is drain, source, gate. So again, here you would have A times of Vx minus A times into. Okay, now here the terminals have been changed. Yes, here terminals have been changed. So this is 1 plus. So AVX हो जाएगा because sorry, V out is A into V plus minus V minus. So here V out is A Vx minus C. So that's why V out would become A times Vx. So Vs is Vx. Here it is Vx minus Vg is A times of Vx plus Vd is Vs Vx minus 0. So ID is Vx Gm 1 minus A plus Gd. Hmm. So here you would get Vx upon ID, that is Gn1 minus A plus Gd, that is minus of Vx upon. So minus of Vx upon ID you can directly use for this. This is Z out 1. Z out is Z out 1 parallel to RL again. Is this clear? The approach?
Uh, yes, so it is GM into, so that should be 1 by GM 1 minus A plus GD, right?
Sorry?
Should it not be like ID is equals to Vx into that we have got? So Vx by ID should be 1 by GM into 1 minus A plus GD.
Uh, नहीं क्या बोल रहे हो? Can you repeat it once again?
Yeah, so in the last three steps, we have
Last three
ID is equals
steps.
to, yeah, ID is equals to Vx into
Oh yeah,
something,
yeah,
right?
1 by ना? हाँ, 1 by
1 by,
1
yes,
by.
yes.
Yeah, 1
Yeah.
by. Vx by वो है ना? इसलिए 1 by.
Yeah.
Yeah. But the method is clear, right?
Yes.
Okay, so let's move on to the next problem. See here in this problem, you have a sine wave oscillator. In this particular sine wave oscillator, the total capacitance in the circuit is 20 picofarads. What should be the value of R such that the circuit oscillates at 1 megahertz? So oscillation frequency is given 1 megahertz, and you have to find the value of resistance in kilo ohms. So total capacitance is 24 picofarad, and we know frequency is 1 upon 2 pi r into c, right? So when your frequency is 1 upon 2 pi r into c, we want, so first of all, for oscillators, there are certain criteria which needs to be satisfied. We call it Barkhausen criteria, where the total phase shift is 0 degrees or 360 degrees. This is one. And total gain, that is A into beta, should come out to be 1. Now, when I mean, what I mean by total gain is, see, in this particular circuit, let's say you are providing input from this side, okay? This is your input, this is your output. So, if you observe very carefully, this particular path, you are moving from input to output, right? We call this feed forward path. And from here you find gain, that is A, which is V out by Vn. Correct? Now, if you observe carefully, there is this another path which is actually connected between your output and input. Can you see this? So this is connecting your output to input. We call this as feedback path. Okay. And how do you find? So basically, when you find gain or let's say transfer function, it is always what is after by before. So here we call feedback path factor as beta and it will be V out upon V in, right? So when I say A into beta should be 1, that means what I address to is this A and this beta.
Beta
Okay,
is Vn by V out, right?
V out by V in लिख दिया क्या? Okay, okay. यहाँ पे V in by V out होगा. So basically, uh, finally you are reaching to V in and where you started was V out, right? So this is the idea. And also when you find the phase shift across your whole circuit, so in one way, like in forward path and then in feedback path. So when you are starting from one place, you come together at that place, the phase shift of that whole circuit should be 0 or 360 degrees. Is this clear?
Yes.
So
So, for
this is,
example, like
yes,
let's say we have just the register path over here. So, I
yes,
mean, there will be no phase shift from V out to V in because it's a purely resistive path,
yes,
right?
yes,
So that means from, I mean, from input to the output, we have a 360 degree or zero phase shift
yes,
in this case,
yes,
particular case.
yes.
Okay,
That is mandatory to
right. Okay.
obtain oscillation. Okay, so this is the Barkhausen criteria. This needs to be met in order to your circuit, like in order your circuit to oscillate. So if you need oscillations, these two criterias are mandatory, and both of them need to be met. It's not like one is like both are mandatory. So both are necessary conditions. Both need to be met. If both are met, then only your circuit will give oscillations. Okay. So now
Yes.
with this information, see what all we know here. We know that, okay, the total capacitance of the circuit is 24 picofarad, 24 picofarad, and we know that the oscillation that we obtain from the circuit is 1 megahertz. And then what we know is the gain of the circuit should be matched. That means if I say what is my V out by V in, so I can say that let's say my feedback path is rather than here, if I say my feedback path is here, so this is my input point. So I can break the circuit anywhere, right? So I'm saying this is my input point, this is my output point, this is my output point. So there is no component between input and output. Why I am doing that? So if you observe very carefully, this gives me like similar circuit. So this is an RC based RC connected to an op amp. Similarly, another RC connected to an op amp. And here it's a resistor based circuit. So first of all, if we break down the circuit, how does this look like? So this is an inverter, right? What is the gain that we obtain from this inverter?
-1.
So inverting op amp with a gain of -1. So here, what is the phase shift that we are obtaining from this particular one only? Phase shift is 180
180
degrees.
degree.
So if we obtain 180 degrees phase shift from here, that means this should introduce a phase shift of 90 degrees. And similarly, this op-amp with 1R and 1C, right? To get a total of 180 degrees. Sorry, yeah, total of 180 degrees from these two. And at the end, we would get a total 360-degree phase shift. Now, in this particular circuit, if this is R, this is R, this is C, this is C, I want same 90-degree phase shift from here, 90-degree phase shift from here. So that means my components would also match, correct? So if I
What does
have,
component matching mean?
so basically I want same 90-degree phase shift from both the op amps,
Oh, okay. Yes,
right? And
got it.
both are connected with one R C and same R and C. So that means this 24 picofarad of total capacitance can be divided as 12 picofarad capacitor over here and 12 picofarad capacitor over here. Correct?
Yes.
This we
So
know.
that is we are looking from the input side for the total capacitance. Is that so?
Yeah, matlab, so there are only two capacitors available over here, right? We are not talking about intrinsic capacitance. These are external capacitance that we are using.
Okay. So I mean, whatever the capacitance in this case will be given, that will be external only, nothing
Yeah,
internal.
yeah. With
Nothing. Okay.
with respect to op-amp, until you are going into the internal circuitry of op-amp, we only talk about external components.
Oh, thank
Okay, only output impedance के terms में we talk about internal resistance, but capacitors are always external in case of op-amp.
you. Right. Okay.
So,
Because
fro-
I mean, yeah, because essentially, like even at the input or any node, op amps are essentially MOS, right? So they will have some
yes, yeah,
capacitance in it.
that's why I said like we are not talking about parasitics over here. We are talking
Right.
about the externally connected uh, capacitors. So
But
yeah,
would
that
this even imply? Sorry, but would this even imply if we have a like a very high frequency as well, or will we talk of the parasitics in that case?
uh, I mean, yeah, if so, it also depends on the operating frequencies, right? Because that's why whenever you talk about an frequency response of an amplifier, it looks like this, right? So we only consider this range as our operational range
Yes.
or bandwidth. The reason
Uh,
being in these other ranges, those parasitics and other capacitors start coming into picture. Like, yeah, all other capacitors because of your interconnects and everything. But
right.
in the bandwidth, we are only talking about the externally connected capacitors. Because when these oscillators are designed, so we want them to be like very specific, right? We want specific frequency oscillators. So for that, parasitics are not in control of us. We cannot control the parasitics value. It's not very easy to control them. But external capacitors, external components can be easily controlled and managed accordingly. So in case of op-amps, especially like when you are dealing with like black box op-amp like this, where you don't know the internal circuit, we are mostly talking about external components.
Right. Okay.
Okay?
Thank
Yeah. So in this, first of all, uh, this particular circuit. So we came to that, okay, 180 degrees is being introduced by our inverter itself. Other than that, we are left with 180 degrees, and since both the op amps are matching with one capacitor and one resistor, that means both of them will introduce a 90-degree phase shift. Correct. So
Okay.
this 90-degree phase shift, for this, we can simply, and since both are same R and same C, and they are connected in this fashion, where it is like R upon minus plus C. And when you find the transfer function for this, so this is your V in, ground, V out. So your transfer function actually looks like, so if it is 0, 0 minus V in by R plus 0 minus V out upon 1 by SC. 0. So SC into V out is minus V in by R. So V out by V in is minus 1 upon RC into S. So this is the transfer function that you obtain because of this particular single filter, right? And since these filters are connected, so we say that these two will provide, like, since everything is same, these two will provide same behavior. So that's why whatever frequency that we are given with, they are appearing at the same pole. So you have two poles at same frequency, considering that they do provide, like, their components are same, right? R and C is same. They are introducing same uh, phase shift. So that means there will be two poles, one introduced by this op-amp A1 and another will be by A2. And those two poles are at 1 upon RC. So from here, you know that F equal to 1 upon 2 pi RC, and this C is 12 picofarad. So from there, 1 megahertz equal to 1 upon 2 pi into R into 12 picofarads. From here, when you calculate the value, you will find the value of R to be 13.26 kilo ohms. Is this clear?
Yes. So just one question.
Hmm.
I mean, is there a way, like you said, these will introduce two poles? So without calculating the function, also can we know? I mean, how, like a quick look at the circuit, and we know will it have two poles or two zeros or something like that?
I mean, it depends on practice. So if you know that this is a low pass filter circuitry, then you know that in low pass filter you will have like one pole coming into picture. Whereas if it was other way around, then things would change. So for example, in the same circuit, what I do is I'll simply interchange the so here there was a resistor followed by a capacitor, right? So
Yes.
let me draw it like this. So there is a capacitor followed by resistor. Everything, all of other things remain same. So this is V out, this is V in, ground. So here 0, here 0. So 0 minus V in, 1 upon SC plus 0 minus V out by R equal to 0. So which brings us to SCVN equal to minus V out by R. So V out by Vn equal to minus RCS, right?
Yes.
So now here it introduces a 0. Now things would be different when you have your input at this point. Things would change because you would
Okay.
solve your equations accordingly. Correct? So it
Yes. Yes.
depends on how your inputs are, like inputs and outputs are connected, how your components are connected. Based on that, you find the transfer function.
Oh, oh, thank
Okay?
you. Hmm.
Yeah. So then moving on to the next problem. So in this problem, you see you have a array of 18 kilo ohms. RB is 225 kilo ohms. Here it is 225 kilo ohms each. Okay. Now what is the CMRR of the circuit given decibels? Right. Okay, so CMRR we discussed, right? What was CMRR? It was
Uh,
common mode
yes.
rejection ratio, correct? Which
Hmm.
was AD by ACM.
Yes.
So AD by ACM means AD is when Vn plus is not equal to Vn minus. Then you have AD. When Vn plus equal to Vn minus, you would have ACM, right?
Yes.
So now let's solve for okay, let's keep them the way they are and let's solve the equations, okay? So this is Vn plus. At this point you will have Vn plus. At this point you would have Vn minus, okay? And this is V out plus and V out minus. So it let's say this is my point A. I'm gonna take some other color. This is point A, this is point B. Okay, you know your point A and point B. Now writing KCL at A. So at A, when you write KCL, how would it look like? So it is Vn plus point. So Vn plus minus Vn minus upon Ra plus Vn plus minus V out plus upon 225K is zero because there is no current going into this. Similarly, no current will be going into this. Now, similarly, when you write KCL at B, it turns out to be Vn minus minus Vn plus on Ra plus, so maybe I'll write Rb. And here it is Vn minus minus V out minus by Rb equal to 0. Now, since both are equal to 0, we can equate both of them, correct? So Vn plus minus Vn minus upon Ra plus Vn plus minus V out plus upon Rv equal to Vn minus minus Vn plus by Ra plus V in minus V out minus upon RB. So here, do you see anything in common? So if I bring these this side, then it would become Vn plus minus Vn minus 2 by Ra, correct? Plus Vn plus by Rb equal to V out plus by Rb. I'm bringing V out to this side. Vn minus by Rb plus, oh, minus V out minus by Rb. So let's keep Vn plus to one side and Vn minus to other side. Okay. Sorry, Vns to one side and V outs to other. So by doing that, it would be Vn plus has 2 by Ra plus 1 by Rp factor, whereas minus, and this if comes this side, so minus Vn minus would have 2 upon Ra plus 1 upon Rp is equal to V out plus minus V out minus by RB. Correct? Now, ED will be V out plus minus will V out minus upon Vn plus minus Vn minus. Correct? So if I simplify this further, I would get V out plus minus V out minus by Vn plus minus Vn minus as 2 upon Ra plus 1 by Rb into Rb. So this will become your AD. Correct? This is clear, right? How we got this? Now,
Yes.
ACM should be like how do we write ACM? For ACM, hmm,
Should
here
we apply
Vn
equal
plus,
signals?
yes, we should apply equal signal to find ACM. So when you apply equal signal, so what would happen is
So no current would be flowing from the
yeah, so
resistor
in
center as
this
well.
particular component, so maybe, so if I talk about this particular circuit, so in the same circuit, if this is like simply V out plus and V in plus, and this is also V in plus, so that means V in plus, V in plus here as well. So there won't be any current flowing through this. right?
Yes.
So if that happens, your V out plus and here both will give you the same V outs. And we know that there won't be any current flowing through this also, right?
Yes.
There won't be any current flowing through this because there cannot be any current flow through this. So which makes like V in plus equal to V out plus V in minus equal to V out minus. So basically both were V in plus, so here both will become V out plus also. So ACM turns out to be 1, right? So the CMRR will become RB upon 2 upon RB into 2 upon RA plus 1 upon RB. Correct?
Yes.
By
Correct.
1. So from here we can simply substitute the values. RB is 225, 2 upon 18K plus 1 upon 225K. So this is 9. Yeah, this becomes 9K. So CMRR is always reported in dBs, so it is 28.29 dBs. Okay, the value of CMRR is 28.29 dBs. Now, is this clear how we solved the problem? This problem is clear, right?
Yes.
Okay, now coming to this problem. So here we have R1 as 16 kilo ohm resistor, R2 as 29 kilo ohm resistor, and R3 as 43 kilo ohm resistor, respectively. What is the input impedance of this circuit? Zn. Give your answers in kilo ohms. Okay, right. So, um, let's say if I connect um, signal input Vx such that Ix is flowing, there won't be any current over here in this branch. The current will flow like this. So it will be Ix, and this current will be slightly divided here, then it will be divided here. Here again the current is 0, and from this path it will go to ground. So here the thing is, in this particular op amp, what you don't know is this component, right? This component is not known to us, like how much will be the current that will be flowing inside the op amp. So let's do one thing. Let's solving like without R1. So if I remove my R1, what is the circuit if I remove R1? So the circuit is basic inverting, non-inverting amplifier, right? If it is non-inverting amplifier, so we know that V out is 1 plus R2 by R3 into V in. So this is how the circuit should look like. So if I draw a simplified diagram, so this is like this. Here you have your R3, here is your R2, this is connected to ground, Now what is happening is we want Z in from here. Okay. What is creating a problem is this R1 positive feedback that has been attached. Now, for suppose here you have a Vx, it carries a current Ix. So there won't be any current flowing through this, so this will experience Ix. This is V out. The problem is this particular part of current, right? So I can find Zn, which is Vx upon Ix. At this particular node, your potential is Vn or Vx. I should say Vx. Yeah. Without R1, we know our V out was this much, right? Now, if I write my this Ix, I can write it as Vx minus V out by R1 as my Ix that is flowing through this, correct? I cannot tell Vx right now, but if my R1 was not connected, I knew my V out was like this, right? So if I write it in that term, 1 plus R2 by R3 into Vx whole divided by R1, then if I separate Vx, I would be 1, that would be 1 minus 1 plus R2 by R3 whole by R1 is Ix. So Vx by Ix is R1 upon 1 plus R2 by R3. So Vx by Ix, which is also Zn, is equal to R1 into R3 upon 2 R3 plus R2. माइनस प्लस में कुछ मिस्टेक हुआ है
Yes, that was
या
1
यहाँ
minus.
पे it was 1 minus no right. So here it was 1 minus, so this would be minus, so this would become R1 by R1 into R2 by R3. So this would give us the Zn. And from here, when we substitute the values, which is how much? R1 1643 by 29. 16 into 43 by 29. So the Zn, what I have calculated, it comes out to be 23.72 kilo ohms. Yeah, 23.72 coulombs. Is this clear how we solved it?
So, but here we are getting a negative uh, Z out, right?
Are we getting negative Z out?
Yes, I mean, if we one and one cancel, that minus sign is gonna bring us
Oh
as
yeah, minus, no? This wala
yeah,
minus. I
yes,
mean,
but
ठीक है, minus does not have much of a significance in terms of impedance because impedance resistance cannot be negative, right?
mm,
So,
uh,
yeah.
and the other thing is like, how did we write just V out just in terms of just one this thing in the equation in between? We find out like if R1 is not present, then
R1 is
that
not
is it.
present, right? So how it will look like?
Yeah, yeah. So that
This
is
is
right.
R3.
But then
Yeah.
in the other equation, why are you putting V out as this? I mean, that is like a part of V out, not the full V out, right?
Yeah, but we have to start somewhere, no? We have to
Yes.
start somewhere. Otherwise, how would we solve? Because the
Mhm.
problem is we don't know, we don't have any information regarding this particular thing, this particular input current. We don't know anything about it.
Yes.
So it's impossible to solve otherwise. So to simplify that, what we did, okay, R1, if it was not there, then we know it's a non-inverting amplifier. So by using that, we know this is correct. This is correct, right?
Yes.
But here, what we can do is in place of V out, we have placed this like the results without our R1 because that is something that we know. And from there, we tried to solve. Otherwise, there is no way out from this.
Can we
So
put
that's
Vx
why.
is equals to Vx at the other terminal?
Where Vx equal to Vx?
So we have Vx at positive terminal, right? Can we put that
Huh.
at negative terminal as well?
Okay, we can put it here as well. Then,
So we'll have equation. Acha, that will be Vx. That will be Vx in terms of V out, right? And
that will give
then
you this 1 plus R2 by R3 only. You can check.
okay, that is the same. Vx is the same. Uh,
Same, right?
yes. I mean, but this is very confusing. Like why? Like we are just putting a part of it. I mean, it's just to solve the question, but
Yeah, it's just to solve the question because the key is that this current is not known.
yeah. So this is kind of.
That's right.
I mean, should I say an incomplete question in its own self?
I mean, yeah, some things must have been given. So maybe let's say the output, the current going inside the op amp at the output terminal, it would have been given. So it would be easier to solve then because the parts we know, then we can solve using. So if we knew this current, this particular current I, then things would have been much easier for us.
Yes.
Yeah, then we would have solved everything in Vx, V out terms and tried to write it in Ix and I terms. Yes. Okay. So are there any problems? So are the problems clear today? Any problem, any doubt? So basically
So
methods are clear, right? How we are doing the procedure because calculation is secondary. You can do the calculations, but procedures are important.
yes.
So yeah, I hope this is clear. If this is clear, maybe we can break over here and meet next week with new set of problems. So that's all for today.
Yeah, thank you.
Thank you.